How did life arise from non-living matter? Nobody knows, but it's the million-dollar question in the current interpretation of the universe. Life is something of an anomaly, and exactly how that transition happened is a big unknown. In this video, we take a look at the Alfred P. Sloan Foundation's initiative called Matter to Life, which focuses on understanding the steps involved in that process. Let's explore their website and see the direction that initiative is taking to answer the unanswerable. Don't forget to stop by CesareProject.com to explore the problems with chronic disease. Here's the webpage for the Matter to Life initiative that starts with a really interesting graphic. It shows something of a progression from an empty glass to life, depicted here as a baby chick. This captures a core conundrum in the physical sciences when considering the challenges of life and understanding biology. The assumption that life comes only from other life dates back to the 1860s, when Louis Pasteur debunked the theory of spontaneous generation. Spontaneous generation depends on the notion that organisms can arise from non-living material, like maggots coming out of rancid meat. In a physical interpretation, at some point, life did come from non-life. This graphic indicates not only that there was no chicken preceding this egg and baby chick, but that either nothing or a rock, which otherwise depicts atoms and energy, somehow gave rise to life. How did that happen? The program's goal is to sharpen scientific understanding of the physical principles and mechanisms that distinguish living systems from inanimate matter, and to explore the conditions under which these physical principles and mechanisms complexified toward life. The first half of this, to distinguish life from non-life, is an ages-old problem of the inability to answer what is life. This doesn't seek to answer that question, but rather understand the differences between them, which is covered in numerous publications from thinkers throughout the ages. The second half, involving conditions, principles, and mechanisms that create a complexity in life, really involve understanding how information flows in living systems. In non-living systems, information flows through them. Metals and inorganic materials conduct signals, but do not act on them in any way. They just deliver a piece of information from point A to point B. Living systems don't do that. They interact with that information and change it and do something with it, which is a fundamentally different problem. In other words, in living systems, information acts on itself, but how does matter facilitate that? This goes on to describe the program and starts with the comment, "Our understanding of the physical world is impressive." Not untrue. It includes, for instance, both detailed knowledge about the history of the universe and a comprehensive understanding of the building blocks of matter. But despite this, we don't have a comparably deep understanding of how those building blocks led to life and organisms. In that case, it's an overstatement to say that we have a comprehensive understanding. Just because we can identify the bricks doesn't mean that we understand them. And clearly we don't, because sometimes the bricks come together to form living organisms, which quite frankly doesn't make any sense. How can life emerge from an information processing matter system? So again, it comes down to information and how it flows and changes and responds to the environment. How does matter do that? And why does it do that? How do living systems harness that ability to interact with its environment and adapt and change in that environment? They seek to understand how the principles that guide order-generating processes relate to the development of functional structures in organisms. There's a general obsession with order and disorder, largely arising from the second law of thermodynamics, which states that closed systems tend to move toward disorder and disarray. Life seems to forestall that process somehow, and while life in many ways appears chaotic, it is also quite ordered, a problem that we've dealt with by installing the notion of complexity. Complexity perhaps being a blend of order and disorder, yet in a useful way that keeps systems together when they should otherwise deteriorate more rapidly than they do. It goes on to ask, what key functions distinguish living from non-living systems? And I'll stop there. We know what functions distinguish living from non-living systems. These include phenomena like intelligence, the ability to adapt, timing, memory, communication, change, and flexibility. The problem is not that we can't distinguish how living systems are different, but we don't understand why they're different or how matter can do that. In order order to extend those principles to matter platforms, we really need to understand not how life arose from a non-living universe, but more importantly, why, a question that we cannot answer in today's interpretation. We know that there's nothing special about the matter that makes up a person versus matter that makes up a rock. They're all the same ingredients. For some reason, the ingredients seem to act differently when it's part of a living system. A function we dump back on the notion of complexity, which is a phenomenon we simply can't explain. It's more of a trash can concept where we identify that something interesting and literally life-changing is going on, but that we have no strategy to explain. This initiative seeks to understand the matter-life nexus. So exactly where the split happens. What are the steps that connect non-living material to make it become living material? It says that the matter-life boundary is not sharp, which I wouldn't call it a nexus then. I'd call it maybe more of a parabola or a curve, perhaps. To explain that phenomenon, they're looking for well-chosen scientific explorations to understand the transition from non-living to living matter. This program has 3 focus areas called Building Life, Principles of Life, and Signs of Life. These areas define a broad scientific scope for understanding the physical principles and mechanisms governing living systems. In other videos, I talk about these governing principles called commandments of life that do exactly this. The trouble is it's hard to understand governing principles when we don't really know how the pieces are moving, like a chess game. Only when you understand what the pieces are doing, how and why, and how they interact, can you find the principles that define the limits of possibilities. Starting way out on the edge, trying to limit possibilities when they seem almost infinite when it comes to life is not particularly effective. If it were, we wouldn't have this problem today. There is certainly no shortage of people trying to do just that. This program supports scientific meetings to promote information exchange, development of collaborations, and self-organizing efforts aimed at making a case for other funders or supporting matter-to-life research. This is ironic. Getting together intellectual beings to promote information exchange so they collaborate and self-organize is exactly what life does. Non-living material doesn't. Before we look at the 3 focus areas, let's check out recent grants. The Carnegie Institution of Washington received one to support a workshop. Syracuse University received $750,000 to perform in vitro experiments related to simulations on attributes of the cytoplasm, which is effectively the goo inside the cell that contains all of the little organelles and proteins that are doing something, in an enzyme-driven active bath and viscoelastic biopolymer network that influences macromolecular phase separation. None of those words sound living at all, which is not surprising because we're starting with non-living material and trying to figure out how it does what it does to become alive. They're not going to find it there. McGill University received $800,000 to study prebiotic chemistry, so chemistry that involves before life, and looking for ways to accelerate chemical reactions important in abiogenesis. So abiogenesis is a new word for spontaneous generation. It means that life arose from non-life. They're not going to find what they're looking for. Johns Hopkins University got $1.5 million. That's looking at biomolecules and chemical dynamics, and I predict it won't break out of a physical interpretation. Gordon Research Conferences, looking at systems chemistry. And finally, University of Texas Southwestern Medical Center at Dallas got $500,000 to use thermodynamic circuit theory to uncover design principles underlying the biochemical networks within organisms and to understand limits imposed by thermodynamics on computational capacity of biochemical networks. If you're starting with thermodynamics, you're going to stay in a non-living universe. One of the troubles with thermodynamics is they don't explain living systems. A more useful approach to this would be understanding why thermodynamics appear to function as they do. Back to the focus areas. These are theoretical and experimental efforts to unravel the physical principles and mechanisms that distinguish living systems from inanimate matter, yada, yada, yada. They are looking for new ideas, but does not support biomedical or disease-related research. This is because they're looking at the matter-to-life boundary in comparatively simple systems rather than animal or social science experiments. that involve complex higher level organisms and their behaviors. So what does this have to do with understanding disease? At the superficial level, it appears unrelated, but it's not. Disease only occurs in living systems. The problem runs very deep in our understanding of what life is and how it arose. As long as we don't understand that, I don't think we can understand disease. People think they're simplifying the problem by getting smaller or looking at individual cells, which are simple cells, and yet it's more complex than anything that goes on with non-living systems. If we want to find principles that explain life, we need to be willing to extend those principles deep into the smallest realms. The principles that govern non-living matter and living matter are the same. They differ in sophistication, perhaps. Rather than starting with known laws of physics and trying to figure out how other things grew out of those is not going to get us where we want to go. If it were, we would have gotten there already. I think the principles we seek start with recognizing the qualities that life has and the things it can do, then simplifying those in the opposite direction. A conversation for another day. The first focus area is building life. These projects focus on learning about life by trying to construct it. Well, good luck when you don't know what it is, you can't recognize it if it were to happen, and you don't have the principles to make it happen. The search for synthetic or abiotic systems that mimic key lifelike behaviors isn't good enough. Computers can already do that, and yet they're not alive. I'm not sure what good this will do. They talk about building protocells and studying far from equilibrium processes, which is another way to say they're more disordered than ordered, and yet they're ordered enough to not totally fall apart. Building entities that demonstrate like-life behaviors. Lifelike doesn't make it life. Example behaviors include replication, metabolism, which is converting energy to do something, evolution, which is change over time, and environmental sensing and information processing that leads to adaptive behavior and cooperative community behavior. Even if a human-made system were able to do all of these things, I don't think it would necessarily lead to adaptive behavior or cooperative behavior. It's left out key elements including intelligence, timing, communication, and memory. If you want to develop lifelike systems, you should probably use lifelike terminology and then figure out how that applies to apparently non-living systems. Sample research questions for this focus area start with non-living matter systems and leverage stored information in building blocks that can do all these lifelike things. So all this non-living stuff is connected to all this living stuff with the word to. That too is a chasm that cannot be crossed with today's way of looking at life. Next is building nanoscale molecular machines capable of complex activities. Well, that's one of the problems, is when you think of life as a machine, you're not going to get anywhere. That's not a new way of thinking. Actually, it's a very old way of thinking that hasn't worked. Seeing smaller into the machine isn't going to fix that. This concept of design principles is interesting because we think we can use principles to design life, which really quietly says that there are principles that designed life before us. How's that supposed to work? Can synthetic cell communities achieve complex functions cooperatively through local cell-to-cell interactions? Can you make nanoscale molecular machines to do this? Sure. Are they going to be alive? No. Can we build a live synthetic cell? If we understood life, maybe. The second focus area is principles of life. These projects focus on identifying the key physical principles that govern living systems, broadly conceived by identifying the principles governing biological organisms. A little redundant, but a matter that I've already addressed. If you want to find those principles, you have to start with living systems and then work backwards. This organization emphasizes starting with physical principles that explain life rather than living principles that might work the other way and explain the universe. However, that idea would require redefining a lot about what we know about the physical universe and incorporating subjectivity, which so far has had zero mention. This program is open to supporting both reductionistic and top-down efforts. Reductionism gets a bad rap. The idea that a system is the sum of its parts. It's not necessarily a bad thing if you're reducing the problem to the right elements. If you're not reducing it to the right elements, it won't work. But that's why there's such emphasis on this term emergent, is because life can be reduced to smaller elements like cells and molecules. But when it goes the other way, when molecules come together, we can't explain cells and larger organisms. The words complexity and emergence are these nebulous terms to explain that in reverse. As for top-down efforts, which presumably means starting with life, then getting smaller, this is to identify the emergent phenomenon exhibited by living systems. Well, we can already observe those emergent phenomenon. Humans can do things that worms cannot do, and worms can do things that cells cannot do, etc. They seek to explain and predict these emergent phenomena at the level of the emergent phenomenon without resorting to more fine-grained processes or mechanisms. This sounds really hard. However, the goal is to meet in the middle and find the key organizing principles and mechanisms that must be implemented in any platform to achieve a living system. In these sample research questions, words like non-equilibrium physics, control, scale invariant physics, quantitative understanding, and state-dependent laws show up in an effort to describe life. The most interesting to me is control. We have an obsession with that, and yet control never shows up with describing living systems. Only humans seem to do that. Isn't that interesting? The final theme is signs of life, to sharpen our understanding of the distinctive signatures associated with living systems and boiling them down to physical principles. There's already volumes available on this. This includes research to determine signatures of life on other planets, other quantitative metrics that can be used to distinguish living from non-living systems. What are the atmospheric signatures? So again, we've come all the way through and not a single subjective quality of life shows up. The only place it showed up was to get people together to promote information exchange, collaborate, and self-organize research projects. In summary, if you want to understand how an empty glass got to this chick, it's not going to be through any progression shown here. The pressing matter is we don't understand why matter can sometimes cooperate and communicate and metabolize information and change. Having an aversion to using lifelike terms to try to explain life is not going to lead to understanding life. Rather, avoiding them and using very narrowly defined terms and thinking that life is going to fit in will lead to disappointment. Perhaps it's time to stop funneling money into experiments that answer what and start really rethinking how and why. One area the current scientific paradigm really cannot function is in the realm of why. As long as it remains so, science will remain full of dichotomies separated by impenetrable chasms. Life, non-life, mind, body, particle, wave. They aren't paradoxes because nature made them that way. They're paradoxes because we don't understand them. In any case, it's time to stop trying to cram life into science and bring science to life. Thanks for listening. Please be sure to like, subscribe, and leave your comments below. See you soon.